In this video, I solve question about first 4 moments about origin of Poisson distribution. Then convert these moment about origin into moment about mean. In other words, we calculate moment about mean of Poisson distribution, and we also calculate beta 1 and beta 2. So now let's start. First moment about origin. By definition, it is represented by mu 1 prime. It is equal to mu 1 prime is the mathematical notation of the first moment about origin. It is equal to expected value of x. When we expand expectation, it is equal to sum of x p of x. So p of x is the probability mass function of the Poisson distribution. It is represented by e power minus lambda lambda power x over x factorial, where the range of random variable of Poisson distribution is from 0, 1 to so on infinity. So put these values. Expected value of x is equal to x range from 0 to infinity. X is the random variable and p of x is e power minus lambda lambda power x over x factorial. Now we solve it. So here we expand our factorial up to one term. So we expand it 1 to 1 term. So we decrease one term here from the random variable. So now our random variable we subtract one digit. So our random variable start from 1 to infinity. We delete 0. So lambda power x, here multiply and divide by lambda. We multiply when you divide, multiply and divide same number. So it has no effect. Mathematically it has no effect on the equation. So I multiply and divide with lambda. Expand the factorial x into x minus 1 factorial. Cut this x with this x. Take lambda outside the summation sign. So lambda e power minus lambda. We take outside this summation sign. This minus goes to 1 plus 1 on the other side. So x is equal to 1 to infinity. And here lambda power x, when this lambda 1 over lambda, when this lambda present in denominator, when we take it in numerator, its power will be lambda minus 1. Add up lambda power x, lambda power minus 1, lambda power x minus 1 over x minus 1 factorial. So again expand x is equal to 1 to infinity, lambda power 1 minus 1 0 over 1 minus 1 0 factorial plus. Put here 2 minus 1 1, lambda power 1 over 2 minus 1 1 factorial plus 3 minus 1 lambda square over 3 minus 1 2 factorial plus so on. Compare this equation with this. E power theta is equal to theta power 0 over 0 factorial plus theta power 1 over 1 factorial plus theta power 2 over 2 factorial plus so on. So we write it as e power lambda according to this. E power lambda. Lambda e power minus lambda e power lambda. Add up these minus lambda plus lambda, cut this. E power 0 lambda e power 0 is equal to 1. So here expected value of x is equal to lambda. Mu 1 prime is equal to expected value of x is equal to lambda. So we calculate here first raw moment or first moment about origin. These are the same names, raw moment or moment about origin of Poisson distribution. Now we calculate second raw moment or second moment about origin for Poisson distribution. Mu 2 prime is equal to expected value of x square. So this x square, look this writing in red ballpoint. If x into x minus 1 plus x, multiply this x inside bracket x square minus x plus x. Cut this x with this x. So we have both sides equal. Left hand side is equal to right hand side. So according to this, we write x square as x into x minus 1 plus x. Now applying expectation. When we apply expectation, both terms, we take expectation single term and the sign remains same at as it is in the actual position. So here is the plus sign, we write plus sign and take the expectation of first number and take the expectation of second number. Expected value of x, we already calculate expected value of x, which is lambda. Now our task is to calculate expected value of x into x minus 1. So expected value of x into x minus 1 is equal to sum of x into x minus 1 p of x. Put the probability mass function of the Poisson distribution, which is e power minus lambda lambda power x over x factorial, and random variable x range from 0 to infinity. So now we expand factorial up to 2 term. So here from range we subtract or we minimize 2 numbers. So our random variable now start from 2 to infinity, and 0 and 1 we delete, because actual range of Poisson distribution is from 0 to so on infinity. So we now our random variable range in second moment about origin is from 2 to infinity, and we expand terms up to 2. So x into x minus 1 x minus 2 factorial, here we multiply and divide by lambda square. We take lambda square outside the summation sign, lambda square e power minus lambda, range of random variable from 2 to infinity, x power lambda power x minus 2, here 1 over lambda square. When take this lambda square from denominator to numerator, it is lambda power minus 2, lambda power x minus 2 over x minus 2 factorial. So when you expand this summation, lambda power 2 minus 2 factorial plus lambda power 3 minus 2 factorial plus so on. So after simplification we have lambda power 0 over 0 factorial plus lambda power 1 over 1 factorial plus lambda 2 over 2 factorial plus so on. So when you compare this, e power theta is equal to theta power 0 over 0 factorial plus theta power 1 over 1 factorial plus theta power 2 over 2 factorial, we write it as e power minus lambda. So by adding, when base same, we add the terms. Here base is e, here also base is e. So add this same base, add the powers minus lambda plus lambda, cut this minus lambda with plus lambda, e power 0 is equal to 1, so lambda square. Expected value of x into x minus 1 is equal to lambda square. We already proved expected value of x is equal to lambda. Mu 2 prime expected value of x into x minus 1 plus expected value of x, mu 2 prime is equal to lambda square plus lambda. Now we calculate third moment about origin or third raw moment, which is mu 3 prime is equal to expected value of x power 3. Mu 3 prime is equal to expected value of x into x minus 1 x minus 2 plus 3 into expected value of x into x minus 1 plus expected value of x. We say this term, this equation as b. So we already solve expected value of x, which is lambda, and expected value of x into x minus 1, which is equal to lambda square. Expected value of x into x minus 1, which is equal to lambda square. But our task is to calculate expected value of x into x minus 1 x minus 2. So now we solve this. Here is the three terms that we solve. Random variable x range from 0 to infinity, x into x minus 1 x minus 2 p of x. So p of x is the probability mass function for Poisson distribution. We write it as e power minus lambda lambda power x over x factorial, and here is the values x into x minus 1 x minus 2. So we expand our random variable up to 3 terms. So our random variable start from x is equal to 3 to infinity, and we delete 3 terms 0 1 2 3, and we expand here factorial x into x minus 1 x minus 2 x minus 3 factorial, and we multiply and divide by lambda 3. So take this lambda 3 outside summation sign, e power minus lambda lambda power 3 summation x random variable from 3 to infinity, because this minus 3 goes to right side, it minus sign convert into plus, when we take one digit move to the other side of the equal sign, then its sign change, plus convert into minus and minus into plus. So this is x is equal to 3 to infinity. Cut these three terms with this x into x minus 1, x minus 2, with this x minus x into x minus 1, x minus 2. And here is 1 over lambda 3. When this lambda 3 which is present in denominator, we take it into numerator, this convert into lambda minus 3. When base same, we add a power, this is equal to lambda x minus 3 over x minus 3 factorial. Expand this summation sign, put here 3 x because random variable start from 3 minus 3 over 3 minus 3, lambda power 0 over 0 factorial plus lambda power 1 over 1 factorial plus lambda square over 2 factorial plus so on. Lambda power 3 e minus lambda, when we equate this is equal to e power lambda. Base are same power, we add the powers, these minus lambda cut with plus lambda, e power 0, as you know e power 0 is equal to 1, so we left with lambda power 3. So put the value of in equation B, mu 3 prime is equal to lambda power 3 plus 3 lambda square plus lambda 4. This is the third raw moment or third moment about origin of the Poisson distribution. Now we calculate fourth raw moment. Mu 4 prime is equal to expected value of x power 4, which is equal to expected value of x into x minus 1, x minus 2, x minus 3 plus 6 into expected value of x into x minus 1, x minus 2 plus 7 expected value of x into x minus 1 plus expected value of x is equal to c. As you know, we already calculate expected value of x into x minus 1, expected value of x into x minus 1, x minus 2. So now we solve here expected value of x into x minus 1, x minus 2, x minus 3. Summation x is equal to 0 to infinity x into x minus 1, x minus 2, x minus 3, p of x. P of x is the probability mass function of the Poisson distribution. So here we have 4 terms, so we start our random variable from 4, we delete the 4 terms which is 0, 1, 2 and 3. 0, 1, 2, 3, because actual range of Poisson distribution is 0 to infinity. So we expand our factorial up to 4 term, x into x minus 1, x minus 2, x minus 3 and x minus 4 factorial. We multiply and divide up term with lambda 4. So cut these values in denominator with the numerator terms and take lambda 4 outside the summation sign. Lambda 4 e power minus lambda, random variable x range from 4 to infinity. Here the lambda 4 which is in denominator, when we take in numerator it is lambda power minus 4. So minus 4, when base is same, we add a power, we write it as lambda power x minus 4 over x minus 4 factorial. Lambda 4 e power minus lambda, when put the value of x which is 4 minus 4 over 4 minus 4 factorial plus 5 minus 4 over 5 minus 4 factorial plus 6 minus 4 over 6 minus 4 factorial plus so on. Lambda power 0 over 0 factorial plus lambda power 1 over 1 factorial plus lambda square over 2 factorial plus so on. It is equal to e power lambda e power minus lambda lambda 4. Lambda 4 e power minus lambda plus e power lambda, cut this plus lambda with this minus lambda which is equal to 0, e power 0 is equal to 1. So we left with lambda 4, expected value of x into x minus 1, x minus 2, x minus 3 which is lambda 4. It is equal to lambda 4. So we prove here first raw moment or fourth raw moment, or we can say it fourth moment about origin of the Poisson distribution. Put these values in equation C. Lambda 4 6 lambda power 3 plus lambda 7 lambda square plus lambda. So this is the fourth raw moment, mu 4 prime This is the fourth raw moment and fourth moment about origin. Now we calculate moment about mean from moment about origin that we calculate recently. So mu1, which is the mathematical notation for first moment about mean, it is equal to 0. Mu2, second moment about mean, mu2 prime minus mu1 prime square, which is lambda square plus lambda minus lambda square, it is equal to lambda. Mu3 is equal to mu3 prime minus 3 mu2 prime mu1 prime plus 2 mu1 prime power 3. As we prove that mu3 prime is equal to lambda 3 plus 3 lambda square plus lambda minus 3 mu2 prime is equal to lambda square plus lambda mu1 prime lambda plus 2 into lambda power 3. Lambda 3 plus 3 lambda square plus lambda minus 3 lambda की power 3 minus 3 lambda square plus 2 lambda power 3. Cancel out all these terms and we left with mu3 is equal to lambda. This lambda 3 cut with this minus 3 plus 2 lambda 3 plus 1 lambda 3. This is equal to plus 3 lambda 3. Cut this with this minus 3 lambda minus 3 lambda 3. And this plus 3 lambda square cut with this minus 3 lambda square. So third moment about origin mu3 is equal to lambda. Now we calculate fourth moment about mean. Mu4 is equal to mu4 prime minus 4 mu3 prime mu1 prime plus 6 mu2 prime mu1 prime square minus 3 mu1 prime power 4. We already solve fourth moment about origin mu4 prime is equal to lambda 4 plus 6 lambda 3 plus 7 lambda square plus lambda. Third moment about origin is equal to lambda 3 plus 3 lambda square plus lambda. Second moment about origin is equal to lambda square plus lambda. Put all these values in this equation. Mu4 is equal to lambda power 4 plus 6 lambda 3 plus 7 lambda square plus lambda minus 4 into lambda power 3 plus 3 lambda square plus lambda into lambda plus 6 lambda square plus lambda square minus 3 lambda power 4. So mu4 is equal to, after multiplication, we cut this mu4 minus 4 lambda 4. This lambda 4 is equal to minus 4 lambda 4. Here is minus 3 and here is 6. 6 lambda 4 plus this lambda 4, 7 lambda 4. Minus 4 minus 3, 7. Cut these two terms with these two terms. So 6 lambda 3, 6 lambda 3, 12, and here minus 12 lambda 3. Cut this 12 lambda 3 with these two 6 lambda 3. So we left here 3 lambda square plus lambda, which is the fourth moment about origin. Here we calculate coefficient of skewness and kurtosis of Poisson distribution. Beta 1, which is the coefficient of skewness, is equal to mu3 square over mu2 power 3. We calculate mu3, which is lambda, and mu2, which is also is equal to lambda. So here lambda square over lambda 3. Lambda square we write it by part lambda square dot lambda, because when base is same we can add a power which is equal to lambda 3. So we write it as, because we want to simplify. Cut this lambda square with this lambda square, we left over 1 over lambda. So beta 1 is equal to 1 over lambda. Beta 2 is equal to mu 4 over mu 2 square. Here write mu 2 square. This is error. Write here mu 2 square. So mu 4 is equal to 3 lambda square plus lambda. Mu 2 is equal to lambda. So write here 3 lambda square plus lambda over lambda square by parts 3 lambda square over lambda square plus lambda over lambda square. Cut this lambda square with this lambda square, we have 3 plus, cut this lambda with this, because here is 2 lambda, lambda dot lambda, we left over 1 lambda. So 3 plus 1 over lambda. This is beta 2. If you like video, then click on like button and subscribe my channel Statisticians Club. If you want to more say videos on the probability distribution, then you can see from my channel Statisticians Club. I already solved binomial distribution completely, Bernoulli distribution, discrete uniform distribution, and you can find their playlist, because all distributions proof I put in one playlist with name binomial distribution, with the name of the playlist, and the playlist is Bernoulli distribution and uniform distribution. Thanks for watching.